We're going to get started. So welcome to the presentation of the 20th Annual Gruber Cosmology Prize. And as you know, this is the final fireworks for a week long of intensive discussions on cosmology. So this is a crowning achievement that we'll be talking about, but the field keeps going. And so that's what we've been discussing for the week, and it seemed fit that this would be the concluding act. So I'm very happy to welcome you all. And now I think this is time for the official part to get started. But welcome in the IAP.
Thank you, Dr. Boucher. I was hoping I'd get to hide behind the podium, but apparently no, it's fine. It's fine. We're excited to be here in Paris, even with the heat wave, and to be part of the CosmoGold Conference. So thank you all for being here with us. The Gruber International Prize Program, established in 2000, recognizes achievements and discoveries that produce fundamental shifts in human knowledge and culture. While we are here to honor Nicholas Kaiser and Joseph Silk, let me mention that they joined Bert Vogelstein and Joseph Takahashi on our 2019 roster. Please note that nominations to the 2020 Gruber Prizes are open until December 15th, 2019, and that we encourage nominations that reflect the breadth of the fields and the diversity of those working within them. Before we return to cosmology, I simply must acknowledge our co-founders, Peter and Patricia Gruber, whose combined vision and leadership established the International Prize Program, and whose attention in doing so brought our affiliation with the International Astronomical Union, and gave us the legs to stand on our own. The Cosmology Prize is presented in conjunction with the IAU, a partnership that has guided our efforts since the earliest days. It's my pleasure now to introduce their General Secretary, Teresa Lago, who will say a few words about this fruitful collaboration.
Thank you, Sarah. Thank you very much. Good afternoon to all of you, even with the whole heat. So, like that? Okay. IAU is pleased to have collaborated with the Gruber Cosmology Prize since the prize started in 2000, it was mentioned. The IAU has an advisory role in the constitution of the Selection Advisory Board, and as part of this collaboration, we receive an annual grant of $50,000 to be awarded to postdoctoral fellows from around the world, so that they may pursue their education and research in the excellent sites in their fields. The Gruber Fellowship Award has been given to young scientists from many countries, a wide range of countries, from Algeria to Chile, Poland, Taiwan, and so on. I will not name them. In some years, the award goes to one young researcher, but in other years, like 2019, the selection is so difficult that we end up dividing the award between two excellent junior researchers. And the fact that also happened in 2019 is interesting because it adds up 2 new countries to the list of the 15 or more countries, and the new countries are Ukraine and France. So the 2019 Gruber fellowships go to Valeria Korol from Ukraine and to Martin Turbet from France. Valerie has just finished her PhD in astrophysics at the University of Leiden. She said she will finish by June, so I believe she has finished by now. And for the next 3 years, she will have a postdoctoral fellowship at the Institute for Gravitational Waves Astronomy at the University of Birmingham in the UK. The winning proposal she submitted to the Gruber Foundation Fellowship is very challenging. She's going to use gravitational waves emitted by ultra-compact object systems to explore the Milky Way and its neighborhood. But even more interesting, she proposes to exploit further the gravitational wave signals, transforming them into music signals and combining them with visual art for outreach activities. Martin Turbot has concluded his PhD in astronomy and astrophysics at Sorbonne University in September 2018. He has recently won the prize for the second best thesis in geophysics in France. He has a Marie Curie fellowship, a postdoctoral fellowship to work at the Geneva Observatory for the future. And his winning proposal to the Gruber Foundation Fellowship is about using three-dimensional global climate models to study the atmospheres of terrestrial-sized planets in the solar system and in other external systems. This is very challenging as well because it does not propose to wait for the big telescopes coming in a relatively short future. It wants to identify the current observations obtained with the currently used working telescopes so that to identify those observations that may lead to the first characterization of the atmosphere of exoplanets capable of testing the existence of life. I wish both a very successful career.
Thank you, Dr. Lago, for being here today. Our relationship with the IAU is invaluable. Nick Kaiser and Joseph Silk were chosen for the 2019 prize by a distinguished selection advisory board that was nominated by the IAU and its affiliate organizations. We sincerely appreciate the knowledge, commitment, and enthusiasm that the advisors bring to the judging process. Let me now invite a member of that board, Subir Sarkar, to present the official citation and introduce the scientific accomplishments of our recipients.
Good evening. So I have the honor of presenting the citation on behalf of the Gruber Prize Committee. So the Gruber Foundation is pleased to present the 2019 Cosmology Prize to Nicholas Kaiser and Joseph Silk for their seminal contributions to the theory of cosmological structure formation and probes of dark matter. Kaiser provided the mathematical description of primordial density fluctuations that have evolved into large-scale structure, while Silk predicted the eponymous damping scale imprinted on the cosmic microwave background anisotropies. Kaiser pioneered the analysis of weak gravitational lensing of light from distant galaxies by dark matter, while Silk recognized dark matter's indirect signatures, such as antiprotons in cosmic rays and high-energy neutrinos from the sun. Their work has transformed modern cosmology. Now, that's what we said in the press release. So now please allow me to make a few remarks appropriate for this expert audience of cosmologists. So Peter Gruber, who with Patricia Gruber founded the Gruber Foundation, which awards these prizes, he believed that cosmology is the most scientifically rigorous and aesthetically elegant and the most poetic of the sciences. Now, I presume all of us in this room quite agree with that. We are not going to object to this characterization of what we do. But I can also, I think, depend upon all of you agreeing that our distinguished awardees today have indeed made what the prize is awarded for, namely theoretical, analytical, conceptual, or observational discoveries that lead to fundamental advances in our understanding of the universe. They have indeed revolutionized modern cosmology with contributions to two of its key topics, dark matter and the cosmic microwave background and large-scale structure. And this conference, which I had the pleasure of joining the last part of, has been devoted to a critical assessment of precisely what has been happening in this golden age of cosmology for the last 10, 15 years. And it's a celebration of the major advances that have taken place and that many of you have contributed to, and certainly all of us have shared in. So I think it is a fitting end to this meeting to celebrate the pioneering contributions by our awardees, which have contributed so much to these successes. So we'll save the personal anecdotes about their lives and careers for the dinner, but for now, I'll stop here. Thank you. So may May I now call upon Nicholas Kaiser and Joseph Silk to please come forward to receive your prizes.
Make a very brief remark. I guess I've been making a presentation after Nick, simply to say that my career has been greeted by having marvelous graduate students, incredible postdocs, and I seem to think that Nick might even be one of those, and incredible colleagues. And over the years, I would say they all, without them, I don't think I would have gotten very far at all, and it's been a wonderful effort over the years to do cosmology with this great team of people.
I think we have another microphone thing for...
yeah, for the presentation, yes.
Yeah. And, is that working? You can hear me? Good. Okay, let me just switch this on. First off, I'd like to...
Put it in your pocket.
Yeah. I'd like to dedicate this to a few people, two of my late mum and dad, who supported me when I was not quite sure what I wanted to do as a young man and tried to do some crazy things, but then finally came back to the correct path for me, which I think was to do physics. I'd also like to dedicate this to my first real physics teacher, Keith Atkin, when I went back to college to do my A-levels, the matriculation exams that I should have done at high school. He just really inspired me. He asked me one day, what do I want to do in my life? I said, I want your job, you know. And, but the other parent is Martin Rees, who I was lucky enough to have as a supervisor. And like many of his ex-PhD students, later on in my career, I would so often reach a point where I just finished some great piece of work, and then it would occur to me, oh, that's what Martin was talking about, you know, when I didn't fully understand it. Anyway, so let me commence with this short presentation. on testing cosmology, which is what I got this gorgeous award for. So I think what I'll do is give a brief historical sketch of how we got here, and then say a few words about these observational tests that we use, being shamelessly advertising my own role in this, so you must understand this is only relatively small. And then say a few things about where I think we are, the current status and problems, and what's the outlook. I better check the time. So this is a picture that cosmologists nearly always show these days, which is very busy and has a lot of things going on in it. It's supposed to represent the model now in which we have 4 phases of the universe. So this all got started, I would say, modern cosmology in the 20s, so just under 100 years ago, when Hubble and others discovered to their great surprise that we live in this universe full of galaxies, and it's expanding. So a huge revolution. Right after that, Zwicky discovered dark matter in 35, right? Incredibly early on. He was looking at a cluster of famous cluster of galaxies. More on these clusters later. And things sort of settled down for a while. Alan Sandage famously characterized cosmology as the search for 2 numbers. That's what he worked on, which is the 2 numbers being how fast the universe was expanding and how fast that was slowing down because of all the matter in it. Though it seems to me that sort of shortchanges the subject, because the 800-pound gorilla in the room was, what is all this dark matter, right? That comes later. So the next big discovery had to wait until 65, when these gentlemen discovered the cosmic microwave background. This meeting this week has been mostly about that and what this microwave background is. It's radiation. It's not particularly important for the evolution of the universe now, but it was super important in the past, right? And it's a fossil of the early universe. And from this radiation, we get a snapshot of the universe as it was about 400,000 years after the Big Bang. Now we're at about 10 billion years after the Big Bang. And this is the famous Planck image. What we're seeing here for the non-specialists is the tiny, tiny fluctuations in the brightness of this radiation. It's almost completely isotropic, but these little 1 part in 100,000 fluctuations are critical for the story that's now going to unfold. What this gave us, though, in 65 was the hot Big Bang model, that the universe had been very hot, radiation dominated in the past, and was now matter dominated. And physicists in the 70s realized that from that you could calculate how nuclear reactions would have happened in the first 3 minutes. That was the title of Steven Weinberg's famous popular book at the time. And amazingly, they could predict that the universe now, or before stars started burning, would be 75% hydrogen and 25% helium. And guess what? That was exactly right. It explained the composition of the stars around us. I really wanted to emphasize this, because we're always trying to push the latest, greatest, crazy idea, right? And I think we give a lot of people, non-cosmologists, the impression that it's just a fairy story, right? And this part of the story is not a fairy story at all. Cosmologists in the 70s could claim quite justifiably that they understood the history of the universe from when it was about a second old to its current age, 17 orders of magnitude. Now, this just gave them confidence to go ahead, and that's where the fairy story starts. But I just want to say this was solid stuff. The other interesting thing they found is that this works in detail only if the amount of normal matter is quite small, and smaller than the amount of dark matter that Zwicky had found. So this is the first indication, became really solid much later, that the dark matter is something totally mysterious. So the Big Bang was a very good working model. Cosmologists used it as a framework for interpreting their observations, but it had some problems to do with its origin. And we called these the flatness problem, the age problem, and the horizon problem. They all stem from one thing, which is that according to the conventional wisdom, for any sensible composition of the universe's expansion would be slowing down. And this was a big problem. Right? So what happened next was a revolution. In 1979, the scalar field from particle physics came to the rescue. The particle physicists had developed the standard model of particle physics in the mid-20th century. And critical to that was this Higgs field, that the God particle, as some people have dubbed it. And this was involved in unifying the weak nuclear force and electromagnetism. At the same time, these particle physicists were mostly believing that at a very early time in the universe, when the universe was super hot, there had been what was called grand unification. Right? And it was in 1979 when Alan Guth was attending a talk by a cosmologist called Bob Dicke, who was talking about the great triumphs of the Big Bang, but emphasized the problems, that Guth apparently realized during this talk that he had the solution. He was working on grand unification. He realized that if at the time of grand unification, part of the universe became dominated by a scalar field, a bit like the Higgs field, then it could start to speed up its expansion. This is an amazing theory which creates all of the matter in the universe out of nothing and explains how the Big Bang gets started. Right? This is the answer to the question, what happens before the Big Bang? Right? And it makes some interesting predictions. I was 79. In 82, the Nuffield workshop happened, which brought together all the great big shots in cosmology to fill in the final part of this theory, which was not only to explain the origin of the universe and all its matter. They argued that if the universe was as smooth as it could be, but had the minimal fluctuations implied by quantum mechanics, you could explain not only why the universe is big and old and full of stuff, but where all the seeds for structure came from. And I think of this as a revolution. And for me, it was important because that's when I was a graduate student at Cambridge. And George, who's here somewhere, drove me over early one morning to go to this famous meeting. And I've spent a great deal of my career trying to confront this kind of theory with observational tests. So in the 80s and 90s, it was wild times. At first, we had a lot of possibilities seemed open. Sadly, along the way, many of them got ruled out by observations. Hot dark matter died. Cosmic strings were a nice idea. Those got killed by observations, and this cold dark matter model came to dominate. Problem with that, however, was that inflation says that omega is equal to 1. That's a measure of how much matter there is in the universe. And stubbornly, the data refused to allow that the amount of matter seems to be about 30% of that. So there were various other problems that people pointed out. And it really gelled. They can probably hear me anyway. Round about the end of the millennium with two things. One was the measurement of the expansion rate of the universe from supernovae and the WMAP CMB observations. One showed that the expansion of the universe is speeding up now. The universe is starting to inflate again. Right? And the other one showed that the universe really is spatially flat. Omega has to be equal to exactly 1. And so we were missing something, the 70%, and that's what we call the dark energy. So what are the observational tests? One comes from this, the cosmic microwave background. You see some small-scale features and you see some large-scale features. And the large-scale features tell us that the basic prediction of the spectrum of fluctuations from inflation is correct, that it's scale invariant. My role in this was to look at much smaller perturbations. Martin said, you should think about polarization, so it didn't mean much to me, but after reading a textbook, I went away and calculated it. And that's about when I got my PhD. Now, at that time, these fluctuations had not been measured. Right? They were a long way from being measurable. And the polarization I'd calculated was a factor 5 times smaller. And so I concluded that it was time to switch gears and move into a different way of testing it. So I started working on galaxy clustering. This is a beautiful picture of a simulation showing how structure evolves and forms something called the cosmic web in the universe. Massive simulation. So it's zooming in on this little region down there where you're seeing a big, what is supposed to be a big cluster of galaxies. And here's some observations of the actual cosmic web in our actual universe, and it looks just like what we see. So the person who had defined the program here was Jim Peebles. Jim said, we've got to measure statistical properties of this distribution, the 2-point function, the 3-point function. He showed how we could use that in the cosmic virial theorem to get the density of the universe. A big problem that he thought was a killer problem for the standard model was the clustering of these clusters themselves. Right? Objects like this. These turned out to be very strongly clustered, and he said, we need some very strange initial conditions. And my contribution in '84 was to show, no, it's very easy to explain that clustering in the standard model. What that led to was some excitement, on my part anyway, was the idea, well, wait a minute, maybe the galaxies are strongly biased in their clustering too. And the hope was that we could somehow get around the fact that the universe didn't look like it only had 30% of the critical density. We wanted it to be 100%, and that turned out to be a dead end. Let's see. At about the same time, mustn't forget this. So again, on galaxy clustering, one thing that I realized in '87 is that when we look at this is a 3-dimensional picture of a slice of the universe, right? It's pizza pie shaped, but the radial dimension, how do we get the 3rd dimension in cosmology? How are we getting the distance to these distant galaxies? We don't have any tape measure or anything. What we're doing is using the redshift, which we know that the more distant objects, the objects that have higher redshifts are more distant, and the ones with low redshift are nearby. That's what Hubble did, and so on. Well, it's true on the large scale here, but whenever you look at actual structures, the superclusters here, they're going to be distorted. And the reason for that is because this structure isn't static, it's growing with time. So the matter's flowing into these superclusters. And so redshift isn't a faithful measure of distance. And that effect is called redshift space distortion. From that, you can measure how fast the structure's evolving. And at the time, we used that to try and figure out what the density of the universe is in matter. Now we use it our colleagues use it to measure the amount of dark energy and so on. Anything that affects the growth rate of structure. So that's 2 probes, CMB, galaxy clustering. Back in Cambridge, our Professor Donald Lyndon Bell had thrown his lot in with 6 others to become the 7 samurai, late 70s, and they thought they were looking at the structure of elliptical galaxies, but as often happens, what they discovered was something unexpected, was that they could measure the expansion of the universe in the local universe, and found it wasn't expanding homogeneously. It looked as though there was a tidal field, and they said, aha, there's a great attractor sitting over there, inconveniently hidden in the galactic plane, that was pulling us. This was very exciting, and I asked Donald if I could have a look at the data and calculate. I said, I want to calculate the likelihood, Donald. And after bugging him a few times, he gave me the data. Unfortunately, he'd forgotten to tell his collaborators, so when I presented the results to them at their group meeting, there was a rather embarrassed silence when everyone looked at Donald and said, how did Nick get our data? Right? So that was interesting. And another thing that happened at the time, which was this idea of using likelihood. All optical astronomers were using frequentist statistics. Chi-squared was normally about as sophisticated as it got. And it had some problems. And so we proposed, let's plot likelihood contours, likelihood functions. And it's kind of weird. We got shouted at by some people who didn't like to throw out the old way of doing things. But it's kind of worrying now that at a meeting like this, everyone is an evangelical Bayesian. Right? There is not a frequentist, there's no card-carrying frequentist left in cosmology, and I'm not sure that that's healthy. Then the fourth probe is gravitational lensing, sort of sketched in this cartoon, that the light we see from distant galaxies has got to us by a slightly circuitous route. And so when we look at the distant galaxies, we don't see them as we should see them. They're distorted by something a bit like a mirage, a gravitational mirage. Tony Tyson pioneered this around about 1990. He showed that you could actually measure this distortion with real observational telescopes. And this just led to a huge amount of excitement and trying to understand what is it he's actually measured. And so I got heavily involved in that. So where do we stand today? Well, the positive things is that what we end up with is lambda CDM model, which seems to work exceptionally well. This is theory versus data from the CMB. It's just embarrassingly good. Here's galaxy clustering, right, where up on the north and the west are observations, 2 different surveys, 3 actually, and on the right in red, if you're not colorblind, is the simulations. It looks just incredibly good, and statistically it agrees as well. What are the cons? Well, we've got a lot of questions. What is the dark matter? We don't know what that is. What is the dark energy? Even less do we know what it is. And maybe the same question may well be, what is the density of the vacuum in physics? Right? That's not known. Physicists aren't able to answer that simple question. Why do these 2 components, dark matter and dark energy, have very similar densities today? Because that wasn't the case all of the time. It seems to be coincidental. There's various other things. It's like neutrinos have a mass. Then that mass has just become important, really. We don't know why there's actually more matter than antimatter in the universe. A bunch of things which we forget about when we're doing day-to-day testing of the cosmological theory. These are big, important questions. So I would say that a meta question is, are these problems really in fact reflecting one single problem, right? Occam's razor said you should search for the most efficient hypothesis to explain things, right? So rather than coming up with a solution for the dark matter and a solution for the dark energy, say, wouldn't it be nice if we could get a common solution? I think that drives a lot of people. And, that's, Occam would say that's good. And it sort of fits with the idea that the history of physics on the broad scale has been discovery of phenomena and their unification. Newton unified the way an apple falls with the moon's orbit around the Earth. Maxwell in the 19th century unified electricity and magnetism. 20th century, the unification of that with the electroweak. So it would be lovely, surely, to have a theory that in a unified way explained all of these problems at a stroke. Maybe, I don't know. But history teaches us it's not always like that. Newton's theory of gravity had to be replaced because it failed in two ways in the solar system, the inner planet and the outermost planets. But it failed for two different reasons. One was dark matter, and the other one was that you needed a new theory. So I don't know. The jury, or at least I don't have a strong opinion there. So what's the outlook for the next decade? Well, it will be a golden age. Well, these instruments I'm showing here are worth their weight in gold, literally, at least the satellites. We are going to have some amazing toys to push forward the kind of observations that I've reviewed well beyond what we thought was ever going to be possible back in the 80s and 90s. Euclid will do lensing, so will LSST, galaxy clustering. Square kilometer array is a bit further off, but there are already precursors to that are starting to operate now. So, and there will be CMB, the Japanese have just confirmed Lightbird. So what can we expect? The pessimistic view is that everything will fit with lambda CDM. Right? In the jargon that we will, the tensions which we have at the moment will be found to be observational error, will go away, everything will be consistent, and W will be equal to minus 1.0000, and it is just Einstein's cosmological constant. And cosmology will become a lot like, in the 40s, 50s, when it was a search for two numbers, it'll become the search for six numbers. That seems to me to be the worst outcome we could expect. I think we can hope for something much better. Perhaps the tensions will become real. They'll become a real conflict. And the current front runner is the tension and the expansion rate, and the best way out of that is to replace lambda, the constant, by a dynamical field. Right? We might see violation of the general relativity prediction for gravitational lensing with these sort of instruments. That would be exciting. And I think the galaxy clusters are going to be particularly powerful for this, for seeing if there are fifth forces, extra forces, acting in the dark sector. Maybe we'll see something unexpected in the structure. There's these hints of something called dark flows, peculiar velocities, a lot like what Donald and his crew were working on, but on much larger scales. Now, we don't take them super seriously, but if those can be done, these are done using something called the kinetic Sunyaev-Zeldovich effect, after Rashid here, and I think that I'm certainly looking forward to what will come out of that. Maybe we'll see something weird in the structure, non-Gaussianity or anomaly. Something that worries me there is I go to meetings, everyone is talking about the same statistic. You've got to measure the bispectrum. Maybe that's a good thing to do. Maybe we're being blinkered. I don't know. Maybe we'll see new light on dark matter. I'm sure Joe's going to talk about this. People are trying to detect the dark matter, but they haven't done it yet. The WIMPs are very popular, but the window's closing. Axions are very well motivated, but haven't been detected. One thing that I like is fuzzy dark matter. I have to admit it's much less motivated, but it has one good thing going for it, that we're either going to rule it out in the next decade for sure, or we'll be able to pretty well convincingly show it's true. And one of the ways we can rule it out is using a recent discovery in gravitational lensing. Here's a cartoon of how we see multiple images of things using the natural telescope of a cluster of galaxies. It turns out if the dark matter in those clusters is this fuzzy dark matter, it's granular. What the observers have measured is they have seen individual stars being microlensed by the dark matter. And the way that happens is super sensitive to the nature of the dark matter. So if this theory's right, I think this kind of observation will fix it. And then finally, maybe we'll have a new theoretical idea. You know, technology has been marching very fast. Right? Astronomy has ridden on the coattails of the military industry who've developed fantastic detectors that we've been able to use, where every decade we've got orders of magnitude increase in power. Moore's law in computing keeps up with that. Right? Ideas are very infrequent. Right? It's Newton in the 17th century. Right? It's French people in the 18th century. It's Maxwell and Boltzmann in the 19th century. And then it's Einstein and quantum mechanics in the 20th century, which is about 80, 90 years ago. So I think there's reasonable hope, looking at that periodicity, that we're a little bit overdue for another surprise. So thank you for your time. I'm not sure if we have time for questions. There you go. Oh, yes.
Yeah, and enter. Thanks.
Okay, so I thought I would give you a slightly complimentary view to what you heard from Nick. I was going to start off with some personal anecdotes about how I began in research, and you could consider this as advice for the next generation. So this is how things were very useful to me. Okay, so how did things begin for me? Well, I would say one rule is that you need more than just intuition to be a cosmologist. And here is a classic example of Fred Hoyle, who had wonderful intuition. He basically, realized the steady state universe in this intuition. We know he was wrong. And here's another example of the great Russian cosmologist, Yakov Zeldovich. So before the discovery of the microwave background, he conjectured the universe was cold, and therefore it was unstable to fragmentation where it expanded, and this gave him a theory of galaxy formation. So he was excited by that. But the interesting thing about Zeldovich is that when the data did come along very soon after, he immediately switched horses. My advisor at Harvard, David Laser, did not. And this was actually wonderful for me because I could test my ideas against his, and that was a great foil. And of course, the person who had the most intuition of all was George Gamow, and his work was largely forgotten until the discovery of the microwave background. Okay, so you need more than intuition. Another rule I would say is that you have to get the timing right. You have to be in the right place at the right time. And so I was a graduate student soon after this. The Bell Telephone Labs had an antenna that was not used for any satellite communication. They gave it to Penzias and Wilson, who discovered the microwave background. And so I was a graduate student in 1964, and this was ideal because suddenly one had a whole new area of unexplored results in cosmology. So this is where I was at the time. This is Harvard College Observatory. I had an office somewhere in the basement. And I spent happy years there working on the formation of the galaxies. So let me sort of tell you what made a major difference to my life there. I attended a summer school in my first long summer there at Woods Hole on oceanographic fluid, astrophysical and oceanographic fluid dynamics. And you can probably see in this figure there are some very famous cosmologists. Let's see, over here you see George Field, Allard Tumri, Peter Goldreich is somewhere there too. And so all of these amazing people were basically giving the students summer projects. So I lucked onto a good one. There I am in the front row, and spent the summer working on the diffusion of photons in the expanding Big Bang. And I managed to get this paper out within a few months. Fluctuations in the primordial fireball, predicting that if theory of gravitational stability was right, that is, if objects formed by gravity in the early universe, one should leave, even though it happened a long time ago, one should leave traces behind in the microwave background, tiny fluctuations that would be witness to this. And incidentally, this was in the days when research of graduate students was actually supported by the US Air Force. Standards were really different then. I'm not sure why they cared about cosmology. I suspect it was more the mathematics that was involved, but anyway, so that was my contract as a graduate student. Okay, so another example that I learned fairly early, I mean, you've seen examples of beautiful simulations of large-scale structure, and so it's, that Nick showed you. So it's true that color is an amazing extra dimension. So now, I was not that great a fan of computers, but this was my attempt early on to understand how galaxies formed in the context of what we called cold dark matter. And so the black line in the center is how fluctuations are growing, and all the red lines are areas where structure can form galaxies, and there are many types of galaxies there. And so this was, okay. Sure, thanks, right, okay. And so this was a wonderful way of connecting observational data and the simplest theory of, as things evolve from right to left, as gravity became more important, one suddenly had these fluctuations peeling off to make galaxies. And then on the larger scales, they were not gravitationally very important to make stars anyway, and one had clusters and groups. So this was a very simplistic idea. And to show you an example of how simple the physics is, so on the bottom right, you see the atomic physics cooling curve, hydrogen, helium in a plasma. And the inverse of that gives you the rate of dissipation of plasma. And all that gives you the reflection of this curve, which contains all the data. And much of what we see today probably is not too grossly different from this. Okay, so here's another lesson, I would say. It's important to choose a new field, ideally interdisciplinary, where there's a gap to be bridged. And so I was very interested in areas with the new experiments to be developed, new theories to be defined. And in those days, galaxy formation and dark matter were certainly two of the outstanding problems. That was then, we haven't solved those yet. And now, not much has changed, but we can add dark energy and polarization of the microwave background as two new areas where we really totally lack any strong theoretical understanding. Okay, so that's the end of my retrospective reflections on my career. Now I'm now going to jump forward and tell you about where I think the future of cosmology is going. And let me sort of begin with dark matter. Okay, so we have these amazing experiments now. So this shows you examples of experiments deep underground in mines where you look for dark matter particles which are weakly interacting. They penetrate the detectors, they scatter them, they should give you some recoil energy. We don't see anything. We look in very faint galaxies, dim dwarf galaxies. The dark matter particles should occasionally give you a gamma ray photon if they annihilate with themselves, which the current theory says they probably should. We don't see that at all. And then finally, here is where the real big powers are at the LHC, Large Hadron Collider. There we collide particles together and try to make dark matter particles, essentially because of they have missing energy or missing momentum, and that would tell you something dark was created by conservation of energy momentum. So we haven't seen anything there either, so it's very, very frustrating. So the upshot is that theorists become incredibly ingenious. So let me tell you about one direction that I've been going in, and that direction is called primordial black holes. So now the beauty of this as dark matter is that we've measured black holes. We're not inventing new physics to make black holes. We saw a beautiful example a couple of months ago with the Event Horizon Telescope, so we know they exist. And if there are enough of them, especially smaller ones, they're an ideal candidate for dark matter. And the reason for that is if I make them very early, then as the universe radiation redshifts away, I'm suddenly left with this essentially component of black holes, which would be very important gravitationally and could be all the dark matter. And so we now are at a state where we are trying to set limits on this hypothesis. And because these black holes do exert effects on stars, and so we're trying very hard now to eliminate all possibilities. So we do have one remarkable window for primordial black holes, which is roughly the mass of an asteroid. Okay, so amazingly, these are produced by inflation models if you go early enough, and there could easily be enough of them. And these are not ruled out by any experiments which come in for the more massive black holes, because the more massive black holes will perturb galaxies, give you too much lensing of background stars, whatever, but these are safe. And so that, to me, is intriguing, known physics, nothing new. On the other hand, there's another school of thought in the dark matter community that is motivated more by particle physics. And so this shows you the parameter space that they work in. And so what you have to realize is that these are all possibilities for dark matter, weakly interacting dark matter particles, and I have enormous uncertainty in the range of masses and the range of interaction strengths. And it's a little bit like, you know, when you lose your car keys at night in the forest, you go to see where you know, you go to see where there's a light pole or something, and you look for them. Maybe you'll find them, maybe you won't. But so we're only looking in tiny preferred areas of this possibly almost infinite parameter space, and we haven't found any dark matter candidates yet. So the question keeps on being asked, have we run out of candidates? And the answer is actually no, because this shows you what we call the WIMP window. So the WIMP is the name for weakly interacting massive particles, and this is a range that's strongly favored by theory. It could give you gamma rays. We haven't seen them yet, but there's this huge triangular window that over the next few years we will gradually fill up and look for these events. So that there's a whole interesting range of activity there to look for dark matter. Okay, so it's far from dead as a field, but we have to keep on looking, I would say, and maybe the primordial black holes are one of our greatest clues. So now let me turn to dark energy. And again, this is a fascinating story. Let me give you the history first. So in Einstein's field equations, he made initially the big step of introducing a constant to balance the experimental universe. That's this lambda term. Subsequent people, notably Lemaitre, stuck it on the right-hand side as a source of essentially acceleration of the universe. So let's go straight to Lemaitre. So this is truly amazing. So in 1934, this was around the birth of quantum mechanics. Lemaitre, who had all of these theories in his notebook for the expanding universe accelerating, he conjectured that the energy of the vacuum was just quantum fluctuations. Okay, exactly the modern theory we have now, with an equation of state that essentially corresponds to negative pressure, and one that in fact would give you suitable acceleration. So this was amazing, and Einstein poo-pooed these ideas very strongly, but the great thing about Einstein was when you showed Einstein some data, he would change his mind very quickly. And so within a couple of years, he and Hubble pose at Mount Wilson, and Einstein says, this is the most beautiful and satisfactory explanation of creation I've ever listened to. Okay, so Lemaitre is very much with us, his ideas, but of course, we haven't got very far in the sense that his prediction was that P equals minus rho. That was the simple prediction for dark energy. And in the early days, this is one of the first experiments, so this parameter that's plotted here, W, is just this -1, and you can see there are huge error bars as a function of matter, okay? And this was from the early data of Saul Perlmutter, one of the papers that merited the Nobel Prize from data at that time. But the amazing thing is we now fast forward to the latest data. This is what perturbs many of us in cosmology. All this amazingly accurate data zeroes in again on -1. There is no indication of any evidence for any new physics, okay? Which you would expect if there was some deviation here, if these different constraints from lensing and dark matter and supernovae did not exactly all coincide. So this is a little bit worrying to when you try to forecast the future. So at some point you have to decide, these experiments are where we are, 2019, but at some point we're going to design much more powerful experiments. At what point should we hope that they will find something different, or be, just accept the fact that they may only confirm dark energy even more closely in the future. Okay, so that's my story on dark energy. And now let me tell you a bit about the microwave background. So this also is an amazing story. You saw these fluctuations, the fossils from the beginning, which embed our cosmic history in the past and since led to galaxy formation. So it's interesting that the two best experiments to date, WMAP and Planck, had tens or hundreds of detectors, and they had a certain amount of sensitivity, millionths of a Kelvin. Remember, this temperature is at 3 degrees Kelvin. So we're looking at variations of parts in a million. But to really go further, you have to do 1,000 times better. This is to look for this elusive polarization signal, which is one of the predictions of the inflation theory. So there are many experiments then being designed now to add more and more detectors, and therefore getting more and more sensitivity, right? And so then you can go below a microkelvin to fractions of that. And so in the immediate future, we have LIGHTBIRD, the satellite just approved. We have the Simons Observatory under preparation, CMB stage 4 about to be funded. We hear balloons too. So all of these are designed to really probe this elusive signal which comes from inflation. However, there is a slight problem with this, and that is there's no robust guarantee of any signal, because we don't actually know when after inflation occurred, when the universe reheated, and the strength of the polarization signal that is predicted that would be a direct test of inflation is highly uncertain. So now this simply means that one should keep on looking, devise better and better experiments, but it's fair to ask, is there another experimental strategy one could imagine using? So let me tell you a little about that in the final part of my talk. So most of these fields, dark matter, dark energy, they share something: no detection, no lower bound. We need accuracy, but also precision, and that's a whole issue. The question is, what do we do next in cosmology? So let me try to give you an example here. Okay, so what you see in red is all the information we have from the cosmic microwave background. So this counts the number of modes in the sky. Okay, so basically, you can add up these modes. That maybe the map of the microwave background sky I showed you had roughly 1 million pixels on it. That means you have roughly 1 million modes, and that's the number, if I integrate under this red curve, the number of degrees of freedom. And so what that means is the limiting accuracy is 1 over square root of n, which is, pretty good, 0.1%. But there's something else which I find incredibly more exciting, okay? So it may be that with this approach, we will be limited in how far we can go, but if you could ever go to the dark ages, okay, then you can look for gas clouds in absorption against the microwave background. And there, because these clouds are very small, they're sort of millions of solar masses, suddenly you have many more modes, trillions of modes. And so what this means is, in principle, one can do incredibly accurate experiments if you go to what we call the dark ages, that is, before there are any stars, before any galaxies. So that's the question that we would like to explore. But it's incredibly difficult to do this. And I'm going to show you a futuristic way of addressing this. And so the idea is the following, that is there some prediction of inflation that we are sure has to be there? And so there is one. We call it primordial non-Gaussianity, that is non-random fluctuations. And so here's an example, 2 examples of random fluctuations, Gaussian and non-random. So the one on the left actually is, of course, the cosmic web. It's a clustering. I mean, we can explain the deviations from Gaussianity by this little parameter in front of delta t over t, and it's of order thousands in those simulations. But if you want to go, but that's all foreground, so you have to dig deep into that to do better. And so ideally, to get to the inflationary signal, it's incredibly smaller. It's, roughly speaking, about 0.01 in these slightly bizarre units. So you've got to do 100,000 times better probably to get down there. And there's a robust prediction for this, depending on the properties of inflationary models, whether they're multi-field or single field. There's a whole literature on this. But basically, you're looking for a signature that's of order 0.01 in this tiny, tiny parameter. And the way you can hope to get that is if you have many trillions of modes. Because then 1 over root n is a wonderful thing. You can really beat things down. And you can never do this with large-scale structure surveys or CMB surveys, never quite get to this level of sensitivity. Now, obviously, one has to do everything to get there. The current limits, FNL of roughly 10, one has to improve this by an enormous factor. Okay, so how do you do this? So there's only one place in the solar system that this makes sense. And this is something for the future. And I would say it's going to involve something very futuristic. So let me summarize again. 1 million pixels on the CMB sky, 100 million independent pixels roughly in my biggest deep galaxy surveys. And suddenly, if I can go to the first clouds and look in the dark ages, I can get trillions of pixels, okay? So in principle, by looking in this time, long before there were stars, right? Here is the last scattering of the microwave background. This is the first stars. So you go back early enough, which means you have to go to very, very high redshift. So you're talking about 21 centimeters. That's the wavelength of atomic hydrogen. And so to go back to this incredibly early epoch, you have to redshift this by, it goes from 21 centimeters to something like 10 meters. Okay, very, very low frequency, 30 megahertz. Okay, so where can you do this? So there's only one place in the solar system where you can have a hope of doing this, and that's the far side of the moon, because this is the most radio quiet place in the entire inner solar system. And it's shielded from all the terrestrial interference. Maybe that would change as we explore the moon more in the future, but right now, the space agencies are exploring ideas to do science on the moon. And so here's a schematic sort of thing. So this sort of radio telescope is really low technology, basically, apart from the computing requirements. You basically lay down strips of printed dipoles over hundreds of kilometers over the lunar surface, radio dipole antennae, and then correlate the signal with satellites and send things back to Earth. Something like that is the idea people are thinking about. Okay, so this is just a concept at the moment. Here are 1 or 2 numbers. you can, in principle, by covering a huge area on the far side of the moon, hundreds of kilometers, have a resolution that is comparable or better than that of the CMB, tens of inverse megaparsecs, and then you need hundreds of kilometers. You need millions of these dipoles to get the sensitivity, and you're fighting against this really bright foreground from the galaxy, which is hugely bright, but it's 1,000 Kelvin or 10,000 Kelvin. You're looking for a 10 meter K signal, but that's not so different from the early days of microwave background astronomy, when we began, with 3 degrees Kelvin, maybe a tenth of that in Penzias and Wilson, and now we're discussing nanokelvin. So in principle, if one's imaginative, one can imagine the future, and in fact, we are planning a dipole. This is the square kilometer array, which will have 100,000 antennae, doing low frequency in 2025. This cannot be used for the moon very well because of the ionosphere of the Earth gives you too much noise. You ideally want to go to a more radio quieter place, but this shows you that we have the technology in place to do this. Okay, so my message really is back to the moon. All this has changed in the past year because in January, the Chinese Space Agency landed a satellite on the far side of the moon, soft landing, with a low-frequency radio dipole. So that you can see that on this. And they are busy taking data on the beginning of the universe. Unfortunately, this was not the optimal satellite for various reasons, but they will do more. The Chinese never give up on these things. They're already planning some amazing experiments the next few years. Meanwhile, the US wants to send astronauts back to the moon. Right now, there's a long way to go. This is the current presence. But the intriguing thing is, why would you want to do this? Look at this amazing image from the Lunar Reconnaissance Orbiter. And Europe's space boss, says that, well, now's the time to build a lunar base. We'll have hotels, lunar village, whatever. And you may say this is absurdly expensive, but if you think about it, the Hubble Space Telescope and the Space Shuttle, they were, 5 to 10, the telescope was 5 to 10% of the space station and Space Shuttle, I would say. So it was a small fraction of the total. And in some sense, doing science on the moon may be a small fraction of the cost of all the infrastructure that might be involved. So that's the message. Maybe in the future, ESA is now launching a call for proposals for the period 2035 to 2050, and we'll be definitely trying to persuade them that the Loon is something they should be thinking about. Okay, so thank you. Many thanks, my postdocs, my students, and above all my family for their support and patience. So over the years, thank you. If there's time, you choose. Questions for either Nick or me? Okay. Sorry? Okay. So I think we'll settle things there. Yeah. Okay.
Congratulations again to our 2019 prize recipients. Thanks to everyone for being here, and do join us for our reception in the foyer. Thank you.
No, maybe not.
Good job, Joe.
Well, you too. I didn't want to try something different. So spy these guys.
Hey, don't forget your...
Yeah. Which one is mine?
figure out whose is who.
Yes. Okay.
It's been long run, so there's somebody there.
Okay. Thanks. Hi. Thank you.
Very nice talks.
Yeah.
And don't forget your medal.
Right. Absolutely. Yeah.
Paper.